Presenting Electricity at Work, a story of heat, light, and power by means of electrical energy. Featuring Dr. Donald P. Brown of the Agricultural Engineering Department of the Michigan State University campus. And now, here's Don.
Greetings, ladies and gentlemen, and welcome to another program. If you've been with us, especially on the past few weeks, you probably remember that we're covering a wide variety of topics on our series here. Not too long ago, we had a program on garden lighting, and following that, we had one on equipping the farm shop. Today, we have something even different from those two. Those of you that are concerned with the use of electric motors around the home and out there on the farm, and I might say, who isn't, know that we always have a problem in starting some loads. Some pieces of machinery are a lot harder to get underway. Sometimes we have trouble protecting that motor. There is a new device on the market that offers a lot of advantages from this standpoint. And to explain it for us today, we have a guest, Mr. Vinton Yardley. Come in, Mr. Yardley. It's mighty nice to have you on our program today, and you have several pieces of material here that you want to demonstrate, so I'm going to get out of the way. I'll be close by if you need me. Just give a yell.
Well, thank you, Don. I appreciate the opportunity to tell your viewers of this new device, which we call a dry fluid drive. Now, actually, this isn't too new because it was invented in France several years ago and has been in successful use over there for years. But it's relatively new here in this country. The device is used for the protection of motors. As a motor is first started, it draws a lot of current. And I want to show you on this little demonstrator exactly how that happens. This little demonstrator consists first of a 1/12 horsepower, 1750 RPM motor. And when we start it, even under no load, as I will now, you'll notice that the current draw goes clear up to the 10 amps or more and then drops back to the running amperage of 2 amps. Now here we go. Now what has happened in this particular time can be explained a little bit better by means of this chart that I have here on the board. This chart represents the starting current and the torque capacity of a normal start squirrel cage motor. When first started, there's a current draw of about 600%. And in this particular case, the current drops as the speed of the motor increases along the line which I am tracing here with the pointer. At the same time, the torque curve of the motor follows a curve something like this. And finally, at 100%, we get down here to the normal operating speed and current. Now, it doesn't make any difference whether this motor is connected to a heavy load or whether it is connected to a relatively light load. We go through this same cycle. The only thing is that this length of time here is greater for the heavy load than for the light load. Now, I want to show you what happens when we have a heavy load in connection with this job. We'll use the same demonstrator, but now I'm going to put a belt on this motor, which is direct coupled to a little flywheel, which serves as the load. Now watch what happens on this ammeter. First, you'll see it go up to a high level and hang there for quite a while before it drops down as the motor picks up the speed. And here we go. You see how much longer it took for this motor to get up to speed under load than it did before. Now, what has happened in this case? We have followed exactly the same situation that we had before, except that we've gone out here and we've stretched out this part of the scale. Now, I want to show you what happens when we use the dry fluid drive. Again, I'm going to have to change my demonstrator a little bit. We'll have to move this belt over on this side. Now, the dry fluid drive is this small piece of equipment that you see hanging on the end of the motor shaft. I want you to note in this particular instance that when I start the motor, the current goes up as it did under no load conditions, drops back immediately. At the same time, this flywheel picked up speed in less time than it did when it was direct coupled. Now here is what happened in that case. Superimposed on this motor torque curve we have the torque curve of the dry fluid drive. As it first starts, it has practically no torque capacity at all. But as the speed gets up, the torque crawls up along this line until finally it intercepts the torque curve of the motor. During all this space in here, the motor is getting up to full speed. It isn't shackled or held back at all by the load. So in this case, we have reduced this particular starting current down to this point before we actually pick up the load. Now, why do we call this a dry fluid drive? We call it a dry fluid drive because of the rather unique medium which we use for transmitting power. The medium in this case is an alloy steel heat-treated shot. And I have some of those shot here that I'd like to show you. These shot are about 17 thousandths of an inch in diameter. And they're so small that they will flow like water. This little can has a spout on it like an oil can. Notice how the shot will flow out of this spout. Just like water. That's the reason we call it a flow charge. Now, I'd also like to point out to you that this shot flows like water as you move it around here, or as I tend to float it. See, they're just little tiny balls. They roll around there just like little ball bearings. Incidentally, if I spilled this on the floor, the chances are we'd all be falling because they are like little roller skates. Now, how does this flow charge transmit power? You're all familiar with centrifugal force. If, for example, I had a golf ball or something like that on the end of a string, I could stand here and I could whirl that golf ball like this. Centrifugal force would cause it to stay out at the end of the string. Each one of these tiny little shot acts just exactly the same way a golf ball would act. Obviously, though, we can't put a string on each one of these tiny shot. But we do the next best thing. We contain them in a rapidly rotating housing. Here is an example of an actual dry fluid drive, full size. This particular dry fluid drive consists of an inner sleeve. Here is the inner sleeve, which is mounted on the motor shaft and keyed there too. On the other end, there is an alloy aluminum housing, which is bolted to the inner sleeve. Now, as I rotate this, you'll note there is also an outer sleeve. This outer sleeve turns freely, independently of the inner sleeve. But mounted on the outer sleeve is what we call a rotor blade. Now, the rotor blade is of a special heat-treated alloy steel, and it has a rather particular shape. Now, this shape is a sort of a wavy shape, something like corrugations coming out from the center. And you can see it, I think, on your cameras now. This blade normally goes in this position, but since I have two of them, I'll take this one off. There is an outer part of this housing which fits over the other part in this position, and it's obvious that we now have a cavity. This cavity surrounds the wavy blade, and that is partially filled. Possibly 60 or 70% of the free volume is filled with this flow charge. Now, as the motor starts, the inner sleeve rotates rapidly, right up to motor speed, bringing along with it the outer housing. As the centrifugal force causes this flow charge to pack around the wavy rotor blade, we get centrifugal force causing the rotor blade to turn. That causes this portion of the dry fluid drive to turn as well. And we have a V-belt sheave mounted on there, which takes the power to the driven machine. We protect the driven machine also, and I'd like to show you how that is accomplished. Again, I'm going to start my demonstrator. I'm going to slow down this driven machine in this fashion. Note how this ammeter shows an increase in load, but it doesn't show an overload like we would get if we had this directly coupled. we have no increase in torque, no increase in current draw, which would cause any trouble. Now, we have some photographs here which show some actual honest-to-God installations. Don, would you like to bring those in? Let's see what we can do with them.
Perhaps I can hold them right here, Mr. Yardley, and you tell us what's in the photograph, will you please?
Well, I'll be glad to. This first photograph is an interesting installation. It's in a cement mill way out west. There's a 300 horsepower, 900 RPM motor direct connected to a fan, and that fan draws the cement off of a kiln. The next installation is a little bit more common installation. This is a commercial laundry washer, such as are used in commercial laundries all over the country. It's a tough load because it reverses, possibly every 15 or 20 seconds. This is a picture of the dry fluid drive, which produces this reversing motion. The next photograph is of a tanning drum used in producing leather. We don't have the drive here, but here is a view of the drive which produces the rotation of that unit, again protected by the dry fluid drive. This is a rather interesting job too. These are telegraph poles in the raw. And the next photograph shows the dry fluid coupling in this case because it connects the two shafts end to end which drive this unit. This is a rather interesting job. It's an overhead crane. Now, overhead cranes are difficult to control, particularly with alternating current, because of the fact that it just simply doesn't give the proper control for operation of that type. Here is the unit which makes that type of control feasible with alternating current. The next unit is a conveyor application. This conveyor was increased in length from about 85 feet up to maybe 390 feet. They didn't want to change the motor. The use of the dry fluid drive permitted the 10 horsepower motor to handle the load without difficulty. The next job is an interesting one too. It's a plastic mixer, and plastics are becoming increasingly important in our scheme of things. Here is the drive which drives this plastic mixer.
Mr. Yardley, you've sort of given us a tour around the country with your photographs. We have a couple we'd like to show you of installations right here on our own campus. If we could take a look at the first picture that we have, shows an installation that Frank Porcening has worked out. Frank has appeared on this program many times, and this shows an application that he's making of this dry fluid drive on a silage conveyor. In fact, we have another picture of this same application there. You can see it just a little better. You all know that the problems we run into with silage conveyors, especially in the wintertime, when the flights may be frozen or material may be frozen in them. So that, I think, is just another indication of some of the versatility of this particular drive. Well, Mr. Yardley, you've shown us a lot of things here today, and I think you've certainly offered a lot of suggestions as to how this little device might find use on a lot of our farms around over the state of Michigan. In fact, we know that they're already using them a lot in industry. Well, I certainly want to thank you for appearing on our program today, Mr. Yardley. We've certainly enjoyed having you, and come back and see us most any time.
Thank you.
To you people out there, we hope that you've gathered some very useful information from this program today, because we feel that there are a lot of possibilities for a device of this type. Time is up, so we'll see you next week.
This has been Electricity at Work. Today's program was presented by the Michigan State University College of Agriculture and arranged by the Department of Agricultural Engineering and the Michigan Committee on Rural Electrification. We had with us today Dr. Donald P. Brown of the Department of Agricultural Engineering. Dr. Brown's guest was Mr. Vinton B. Yardley of the Dodge Manufacturing Corporation. Today's topic, a new electric motor drive. Electricity at Work is directed by Jack Caldwell.